All right, so welcome back from break, first of all. You guys were supposed to do that Chapter 7 preview assignment. Most of them were odds. Should not have taken too much time for you to refresh your memory. The main thing that you guys need to be able to do is the Gaussian reduced to echelon form on the calculator, and then also a refresher on just how to solve systems of 2 and 3 equations by hand if you need to. That's kind of the biggest thing that you need to be able to do. There was one little trick that you probably hadn't seen before, and so we're going to do that one in class. That was number 78, and it was actually the even problem that you wouldn't have been able to check your solution to anyway. So now you can check your solution. I am going to run through this pretty quickly since you were supposed to have already tried it. Okay? So first of all, this is a word problem, and we want to solve this with a system of equations. So we need to start writing some equations to describe this scenario. Let's let x equal the number of liters that we're using for the 10% solution, y be the number of liters that we're using for the 25% solution, and z be the number of liters we're using for the 50% solution. Okay? What is the easiest equation that you can write with x, y, and z? Right. X plus y plus z should equal 40. Right? What's another equation you can start writing? So this equation talks about the total number of liters we're using. Now if I want to talk about the number of liters that are acid, how can I write an equation that talks about the number of liters that are specifically acid in my whole solution? 0.1x, good. That will give me the number of liters that are acid in my 10% solution, plus 0.25y will give me the number of liters that are acid in my 25% solution, and 0.5z will tell me how many liters are acid in my 50% solution. What does that equal to? 12.8. And how are you getting 12.8? Yeah, you're taking 32% of 40, right? Because remember, you're supposed to be talking about how many liters are acid. So if you want to find the number of liters out of your total solution that are acid, you should have 32% of your 40 liters are acid, right? So 32% of 40 is 12.8. Are there any questions on that? Okay, notice that you don't have a relationship for a third equation, but we have 3 variables. That's kind of what the trick is to this one. There is not a third equation that you can write. All right, so you do, it says at the very end that they want to use as little of the 50% solution as possible, but that's not really an equation. That's an inequality, so we're going to have to wait to the end on that. The tricky part here is that you can still use Gaussian elimination on this to solve this problem. The difference is that you will not get a full diagonal of 1s and then 0s elsewhere with this kind of Gaussian elimination. So let me show you what happens. First of all, when you write this system as a matrix, you get 1, 1, 1, 40. And then you get 0.1, 0.25, and 0.5, 12.8, right? Okay, when you convert this into reduced row echelon form, what'd you get? Should have gotten 1, 0, negative 1 2/3. Anyone here? Did anyone get this far? No? Okay, and I'm going off of memory, so I have to redo this. Why don't you guys get out your calculators and do this with me? Go ahead and type in that first augmented matrix. So you'll need to go in and edit a matrix A. What are the dimensions of our matrix that we're putting in? So this one will be a what? 2 by 4. Yep. This one was in the calculator section, yes. All right. So then we're doing 1, 1, 1, 40, and then it should jump you down to row 2. 0.1, 0.25, 0.5, 12.8. Quit out of that. Pull up your reduced row echelon form. This was what you guys were supposed to practice, so you should be able to do this. You guys should be getting, and I'm writing, they're giving it to you in decimals, but when I see 0.6 repeating, I know I can write it as an exact fraction if I write it as negative 1 2/3. And then I've got the solution negative 18 2/3 on that row. Okay, on my bottom row, I get 0, 1, 2 2/3. And then I get the solution 58 2/3 repeating, right? Now, I'm going to figure out here in a little bit, and I kind of already know, but this is going to be easier if I have these in improper fractions. So I'm going to take a second to rewrite this in improper fractions. If I do, I get 1, 0, negative 5/3. That 18/3, if you were to convert it, you would get negative 56/3. On the bottom, we get 0, 1, and 8/3. And then the 58, do your conversion, that's 176/3. So these numbers are going to be a little bit easier to work with. Okay, so now the trick here, you guys, is that you didn't get ones down the diagonal. When you get ones down the diagonal and zeros everywhere else, that's what allows you to say, like along the top row, that you have 1x equals a certain solution. And then on the second row, 1y equals a certain solution. The problem here is that I don't just get 1x. Like right here, this equation would be 1x, but what else do I have? Negative 5/3 z, right? I've added in a z piece that I don't really want there because I didn't have that third row. But remember, we're trying to choose z so that it's the smallest, right? Once I know what z is, could I figure out what x should be here? Pretty easily, if I know what I want z to be. Right? Because then I would lose that variable and all I'd have is x is equal to however many z's and then that, right? Same thing down here, I'd have 1y, however many z's, and that. So the trick here, you guys, is that this equation, these two lines tell us, this one right here says that x is equal to 5/3 z minus 56/3. Take a second and make sure you follow that with me. So I added, this is a 5/3, this represents negative 5/3 z, right? I'm adding it over, this bar is like an equal sign. So I'm adding it over, and then that minus 56/3. And that's this 1x, right? So what would 1y equal? Negative 8/3 z, right? Plus 176/3. Do you guys see what I'm doing there? This 8/3 is in the z column. So you're subtracting the 8/3 over in terms of z plus 176/3. Right? So now we have the flexibility of if I can figure out what z should be, then I can figure out what x and y should be, right? So now the trick is, what do you know, what constraints do you know about x and y? They have to be, what? In general. Can x equal -1? Right. We're talking about the number of liters, right? You can't have a negative number of liters. So x and y both have to be greater than or equal to 0. They could equal 0. That's possible, right? But they can't be less than 0. So that's what's going to kind of help us figure out what z could be. I know that I've got this restriction that my 5/3 z minus 56/3, I know that that has to be greater than or equal to 0. I also know that negative 8/3 z plus 176/3, that also has to be greater than or equal to 0. So then I'm going to solve both of these inequalities to see where I'm being restricted for z. So on both of them, I'm just going to leave my z on the right or left-hand side. So I get 5/3 z is greater than or equal to 56/3 on this side. Over here, I get negative 8/3 z is greater than or equal to subtracting negative 176/3. What can I do on both of these? Can I clear out those fractions pretty easily? Yeah, if I were to multiply all of this stuff by 3, I'd lose the 3's on both sides, right? That 3 would cancel all the denominators. So what is z over here? Z is greater than or equal to 56/5, right? And on the other side, careful, z is less than or equal to, because I'm dividing by -8, I have to switch my sign. And then the 2 negatives will cancel and I'll have 176/8. All right, now these two things together tell me that z has to be less than or equal to, if you divide 176 divided by 8, I believe you get 22. But z has to be greater than or equal to this constraint, right? Z is greater than or equal to, and if you were to do this, you would get 11 and 1/5, or 11 and 2/10, right? So 11.2. So what is the smallest that z can be? Right. So I am choosing, because I want, specifically it says up here, as little of the 50% solution, that's my z, right? Z represents how much of the 50% solution I'm doing. So I am going to choose this value for my z. Okay, how can I find x and y then? Just plug it in to these equations, right? So x is going to equal 5/3 of my 11.2 plus or minus 56/3. That actually gives you 0. Yep, we're not going to use any of the 10% solution. Sorry. And then, what's an easier way to find how much y we're going to use? Rather than plugging it into this whole thing and doing that ugly computation, what do x, y, and z have to add up to? 40. I'm not using any of x, so wouldn't it be easier just to do 40 minus 11.2 to find y? Okay, and what is that? 20 what? 28.8. So we have solved the problem. We know that the least amount I can use for the 50% is 11.2 liters. If I do that, then I'm not going to have any of my 10% solution, and I need to mix the 11.2 with 28.8% of my 25% solution. Are there any questions on that? So that should have been the hardest problem out of those reviews. And again, the biggest thing is, you know, this Gaussian elimination thing. All right. So having done that review, we're going to move on to section 7.4. We're going to be dealing with partial fractions. You're using that reduced row echelon form for the matrices to decompose rational functions into partial fractions with just linear factor denominators. We'll be able to check if our decompositions are correctly by doing an algebraic check and also doing a graphical check. And the other thing we're going to look at is how can I use partial fractions to give a rough sketch of a rational graph. So if you'll remember way back in the day, semester 1, when we graphed rational graphs, you guys had to find horizontal asymptotes, vertical asymptotes. You had to plot a lot of random points to see what that general shape was, right? You had to plot in every single chunk of your graph to see what kind of a shape your graph gave you. We're going to give you a way that you can quickly check whether that shape is correct. You ready? Yeah? Okay. Hold on. So let's look at, we only have 3 examples, so let's move through them. All right. Whoa, sorry about that. So here I give you a rational function, right? And I want you to decompose it what I mean by decompose it is I want you to break the denominator into different factors. And then I want you to, instead of writing this as one big fraction, I want you to break that apart into a bunch of small partial fractions for each factor of the denominator. So let's see what that looks like. What can I do to factor out this denominator? How can I factor it? Yep, x minus 3, x minus 5, right? So we're looking at that instead of this. So your first step is going to be to break this into factors. Then what you want to do is write a series of fractions that could represent any denominators that could be a part of that. Okay? So basically, I'm going to say that this thing equals some fraction. I don't know the numerator yet. I'm going to be working on that. But I have a denominator that could be x minus 3, right? And then if I wanted to make sure that I have something that adds up with a common denominator of x minus 3 times x minus 5, I need to add on another fraction that will force the x minus 5 part of that denominator. So would you agree that I could find some numerators, a and b, that if I add these two fractions together, when I force the common denominator, I can make that numerator be 2? Right? I'm basically breaking this down. So the question is, well, how do we do that? Okay, basically, you multiply this entire thing by the common denominator, which should always be this whole thing. All right? So if I multiply this fraction by the whole common denominator, then I lose that whole denominator, right? So in other words, this drops down to 2. If I multiply this whole denominator by this fraction, what do I lose? X minus 3, right? But I'm left with a on top, and I'm still left with an x minus 5, because that did not cancel. Do we all see what I'm doing here? What's my last bit then? B times x minus 3 is the part that didn't cancel there, right? All right, so here's the trick. You have got x terms and you've got constant terms. You want to group them accordingly to that. So currently this side is grouped by a's and b's. You want to spread this all out and regroup it in terms of x's instead of those capital letters. All right? So in other words, I'm going to just take a second and distribute that a through and write this as ax minus 5a plus bx minus 3b. And I now want to group based on my x's. So where are your terms that have x's? And what are the coefficients on those? So here you have an ax, so I'm going to steal the coefficient as a. Where else do you have an x? Bx, so I'm going to add b, and I'm going to pull the x out and write that as just one whole term. Do we all see what I did there? Okay. The next thing I'm going to do is write my constant terms as one whole group. So notice that my constant terms is this whole negative 5a and this whole negative 3b. What you want to do is compare this side to what you want the numerator to be. So how many x's do I have on this side? How many? You have 0 x's technically, and I'll write that in just so you can see it, right? If you have 0 x's, then what should a plus b be? 0, right? If I want these two sides to match, then I want to have 0 x's, meaning I want to have a plus b be equal to 0. Okay? What do I want negative 5a minus 3b to equal? Huh? 2. Yep. I want this constant on this side to match this constant on this side. You now have a system of equations that you can solve, right? You can do this. It doesn't matter to me. Sometimes it's going to be quicker just to go through and do it by hand. Sometimes it'll be quicker to do it in Gaussian elimination. All right? It's up to you guys. You just are solving the system however is quickest for you. In this case, do you think it's faster for us to go to our calculator or just to jot it out by hand? I would say just jot it out by hand, right? And actually, I think most of them today are easier by hand, but we'll see. So you'll notice here, what does A equal if I solve for it? Negative b, and then I can plug that into this equation, so I would get negative 5, replacing a with negative b, all right, so now on this side, negative 5 times negative b is going to be positive 5b, minus 3b is going to leave me with positive 2b on this side, so that b is equal to 1, and if b is equal to 1, what is a equal to? Negative 1. So that one was easy enough just to kind of go through and do by hand, right? All right, what that means is that I can then come back up here and say that this right here then, I'm just plugging in my a and my b. So that means that this is negative 1 all over x minus 3 plus 1 all over x minus 5. So what I am claiming here is that this original part right here is exactly equal to this function decomposed into these two parts. Okay, now what did I say to do next? To check it, yeah? And how do we do our algebraic check? What did I say to do? It says to combine the partial fractions. So basically you're acting like I gave you this and I told you to put it together as one fraction. So if I told you to put that whole thing together as one fraction, what would you do? What would you do to the negative 1 over x minus 3 in order to combine these? What would you do? Multiply it by? Right, you would be multiplying the top and the bottom by x minus 5 to force the common denominator, right? Okay? And then what would you do to the 1 over x minus 5 piece? Yep, you'd be multiplying that one by x minus 3 over x minus 3, right? So that they both have the common denominator and you can put them together. All right, so take a look at what happens. On top, you're multiplying a negative through, right? So you're going to end up with negative x plus 5 from that fraction. Over here, it's just a plus 1, so we actually end up with just plus x minus 3 all over x minus 3 times x minus 5 for my common denominator, right? So what happens in the numerator? Yep, your x's cancel. 5 minus 3 is 2, and then if you FOIL out the bottom, you get x squared minus 8x plus 15. Is that what I started with? Yes, so then that is your algebraic check that your decomposed parts actually do equal what you started with. Any questions on that? No? All right, let's take a look at another one. Notice that this time I'm still asking you to decompose the partial fraction, but now I'm asking you to support your answer graphically rather than checking it algebraically. Okay? Still go through the same work first. The ending is going to be what's different. So what do I do first and foremost on these problems? What's my very first thing? Factor the denominator or numerator? Denominator. Yep, you do not want to factor the numerator. Even if it can factor, you don't want to. What does this denominator factor into? X squared, yep, you can pull out that x squared, and then you're left with x minus 3. So that's replacing that, right? Then what do I do? Huh? Okay, and then here's where we have to be a little bit careful. We have to do every single denominator that could be a fraction, that could be a part that leads into this. Is it possible that I have a denominator of just x and not x squared that could still lead me into this kind of a thing? That is still a part of that common denominator. So in other words, if I write a over x, is it possible that I could have a fraction with just x on the bottom and still get this common denominator? Everyone see that? Yes. So basically, what the trick is here is that if you have a factor that has a power higher than 1, you need to include all powers of that factor. So if something is to the 5th power, then you need to include 5 fractions. 1 to the 1st power, 1 to the 2nd power, 1 to the 3rd power, 4th, and 5th, right? Does everyone see what I'm saying? So this one, since I have a power of 2, I'm going to include 2 fractions. 1 to the 1st power, 1 to the 2nd power. It could be just an x term that's squared, but it could have been also this x minus 3. So I might have had to do an x minus 3 term and then an x minus 3 squared term, if this had been the squared piece, right? That's possible as well. Just watch that if you have higher powers on your factors, that you are putting however many powers there are, that's how many fractions you need for that factor. Okay, am I done? What else do I need? Yep, plus c all over x minus 3. Now that only had a power of 1, so I should only have one fraction for it. All right, so now we start to do the clearing the fraction. So on this side, you should always be clearing that whole denominator, which should just leave you with your original numerator. So that will be 3x squared minus 4x plus 3. What is left with my a term? What am I multiplying a by? So you're asking if I multiply this red stuff on top of this, I cancel one of my x's, right? So I'm still left with 1x and the x minus 3. What am I left with for my b term? Just the x minus 3. Yep, the whole entire x squared term would have canceled on that one. What am I left with for c? Just the x squared. Yes?
Why is it x cubed on c?
Because I only have an x squared. So the only thing that's canceling is the x minus 3, right?
Oh,
And then it's left with an x squared.
okay.
Now what do I do? Start distributing everything. Yep, get them all separated out. So I'm going to have ax squared minus 3a plus bx minus 3b plus cx squared. Okay, now what? Yeah. Yes, there should. I'm sorry. Let me squeeze that in. So 3ax plus. Thank you. All right, now what do I do? Group them by what? How am I choosing how to group them now? By your x's. So what's my highest power of x? X squared. So you want to look for those coefficients. So I've got ax squared, so I'll put an a, and I also have cx squared, and it's positive, so I'll put plus c. That whole quantity represents my x squareds, right? Okay, what should go in my x grouping? What? Almost. Negative 3a plus b x, right? And that was from this negative 3ax and this bax. What makes up my constant? What's the only coefficient I have for a constant? Negative 3b. Yep. And there's my constant. So I've used everything. All right. Now what? Why did I do that? Come on, guys. Why did I do that? This should not be overly difficult right now. Yeah, so now you set it equal to the matching coefficients. So in other words, I'm going to take a plus c and set it equal to 3. What are my other equations? This shouldn't be hard, guys. I should be getting a little bit more response from you. Negative 3a plus b equals negative 4. What's my last one? Negative 3b equals 3. This is another one that will be easy enough to do by hand, right? From this, what do I know that b is equal to? Negative 1, just by dividing by negative 3. Once I know what b is equal to, can't I do, plugging it into the other one, negative 3a minus 1 is equal to negative 4, right? Plugging it into the second equation. So then I get negative 3a is equal to negative 3, so that a is equal to 1. And then to find c, I know that a plus c, which I can just plug a in right away, is 1, plus c should be equal to 3, so c is equal to 2. Take that back up to your original partial fractions and plug them in. So what I am claiming is that my partial fractions are 1 over x minus 1 over x squared, plugging in a and b, and then c is plus 2 over x minus 3. All right. Now, I want to check this graphically. What this means is that you plug into your calculator. And let's see here. What you plug into your calculator is go to your y equals. And for y1, plug in your original equation. You should be putting parentheses around your top. So you should be putting parentheses 3x squared minus 4x plus 3, parenthesis, divided by, parenthesis again, your original denominator. So x cubed minus 3x squared, and then end your parenthesis again. Graph that, and then draw a quick sketch. I would just graph that, you guys, on, and I'm trying to plug it in real fast here. I would just graph that on a 10 by 10 grid. Okay. Draw a quick sketch of what you get on the 10 by 10 grid. So I'm getting something that looks like this. You agree? So then to check it with your solution, all you need to do is for y2, plug in 1 over x minus 1 over x squared plus 2 over, and then make sure you put parentheses on that last denominator since there's more than one term. It needs to know to include it all. Go ahead and plug that in, unhighlight your y1, and check to make sure you get the same graph. And you should get that same graph. If you don't, then just check how you plugged it in. But that's your graphical check, is to plug in the original equation, jot down its graph real quick, plug in the partial equations that you got, and see if it matches it. And it should in this case. Again, make sure you're putting parentheses on that last denominator since there's more than one term so that it knows to group the 3 in the denominator as well. Are there any questions on that? All right, one last example. And you might have to stay 2 minutes after the bell for me to finish it, so just be prepared, but it shouldn't take too much more than that, or any more than that. Okay, notice on the last 2 examples that we did, you guys, you got denominators in the numerator, I'm sorry, that doesn't make sense, powers in the numerator that were always less than the power in the denominator. Notice that here I now have a power that's equal, right? If you have a power on top that is equal to or greater than the power on the bottom, you're going to have to use long division first and then just break up the partial decomposition on the remainder. So let's take a look at this. If I do long division on this, I get x squared minus 1, long divided by 2x squared plus x plus 3. So in order to get 2x squared, I'd have to multiply this guy by 2. Multiply that through, I get 2x squared minus 2. But remember, when we do long division, we change the signs so that we get a cancellation, right? So then what's left over is x plus 3, and that, or x plus 5, and that's actually as far as I can go because now this power is too big for me to multiply to a lesser power, right? So that long division actually went by really quickly. What that means is that my original fraction is actually the same thing as saying 2 plus, so my quotient, plus my remainder, and what do I put my remainder over? What does the remainder go over? The divisor, which is, what's my divisor here? Yep. And now what we're going to do is break this piece apart. All right? So let's really quickly go off to do the work for that. So if I'm looking solely at this piece, whoa, hold on. How can I break up that denominator? X minus 1, x plus 1, and then I would go through my partial fractions work. So I would say that this could be a all over x minus 1 plus b all over x plus 1. I don't have any higher powers on those factors, so I can just leave it as that. Yes? Oh, yes. Sorry, I dropped that. Thank you. If we go through and we clear the fraction, then I lose the fraction on the first piece altogether. The a term is just left with x plus 1, and the b term is just left with x minus 1. Start grouping that. I get ax plus a plus bx minus b, so that my x terms are a plus b x from these guys, and my constant term is a minus b from those guys. So what are the systems of equations that I can write for this? Oops. Yep, so we can write a plus b equals 1, because I'm trying to set this equal to x plus 5, right? So I should have 1x. So a plus b should be 1, and then a minus b is my constant, so that should be 5. What's the easiest way that you guys see to solve this? That's pretty well set up for elimination, wouldn't you agree? This gives me 2a equals 6, so a equals 3. And if a equals 3, what should b equal? So that, yep, b should be a negative 2, so that when I take a plus b, I get positive 1, right? So basically what I'm saying here is that this thing right here can become 2 plus, and then those partial fractions. So the a piece being 3 all over x minus 1, and then minus 2 all over x plus 1. This is what I'm claiming is my partial decomposition. Okay, now it says to do this to come up with the graph shape for that original rational. And here is how we do it. What you guys want to keep in mind on this is that remember that if I gave you the graph 1 over x, do you guys remember what the graph for 1 over x is? Looks like this, right? Remember that? Okay. And how about if I put a negative in front of it? What does this negative do over here? Flips it vertically, so this chunk would have the general shape opposite of the other one because of that negative, right? Basically what we end up doing is putting those two together with just a few more pieces of information. So all of this tells me a couple of things. This whole graph, whatever non-rational pieces you have left over, this tells you where your horizontal or oblique asymptote is. So if you get an x term in here as well, you're going to have a slanted line. That's an oblique asymptote. In this case, you just have 2. So that's a horizontal asymptote at 2. Okay? This piece says, do you guys see where the vertical asymptote is here? On this piece, what's the vertical asymptote? Positive 1, right? Okay? Centering around this asymptote in the horizontal, I'm expecting this shape about that asymptote. So in other words, on this vertical asymptote, I'm expecting this shape on one side, and then I'm going to be expecting this shape on the other side. But I'm also going to have to put that together with this. So let's just really quickly draw that in. Where's this asymptote? Negative 1. Okay, this asymptote is following this general shape. So I'm expecting a high quadrant to the left of that, and then put these two things together in the middle. So on this piece right here, I'm expecting a low shape, and that's actually going to finish connecting with this low shape. So in other words, this part of the graph was supposed to be doing something like that. This part of the graph was supposed to be doing something like this, so I know I have a U down in here. Does everyone see that? So you're kind of using this, whether it's this or its reflection, and piecing it together with a horizontal asymptote as well. And this is a general graph, but that went pretty quickly, right? All right, your homework due tomorrow, or I guess on Wednesday, is this guy.